So as a VLSI engineer, if you want to design a circuit, then there will be probably two important things, and those are performance and the power. And if you want to, if you consider the current scenario, then I think power is the main thing. You can achieve a great performance in cost of the power, but again, if your device can't run on low power, then people won't buy it. So that means as a VLSI engineer, you need to have a great knowledge, a deep knowledge on how the power consumption is happening in CMOS device. And as all the CMOS devices are practically born out of inverter only, CMOS inverter only, so if you know how power getting dissipated in how many way, then probably you can easily calculate power for other circuits. And if we come to CMOS inverter, this is our favorite inverter we have. Now the basic thing, and that is your power is equal to V into Y. So there must be a voltage difference and there must be a current flow, right? And we know from our earlier discussions that in CMOS there is no path from VDD to ground to flow any current in rough scenario, right? That means we can say roughly that hey, CMOS consume zero power, because for first half our PMOS would be on, NMOS would be off, and vice versa for the second. But hey, this is not a true case. Actually, I used to think like that, but here we have three scenario when your CMOS will consume power. And the first scenario is your dynamic power dissipations. We will explain what they mean. Second is during your steady state, when our signal is not changing, but at that time for sure there won't be any power dissipation, but due to leakage we say that hey, our NMOS is off, but ideally it won't be off. There would be some nano ampere of currents are flowing, and if currents are flowing, imply voltage difference are there, imply power dissipation is going to happening, so which we call as leakage current. And the third is that, and that is very ugly name, and that is your short circuit current. We have discussed this thing, like if this is your inverter VTC, then there is a scenario where your NMOS and PMOS both are on. So at that exact moment we have a direct path from VDD to ground, and therefore a short circuit, because the VDD is connecting with the VSS, so that is called a short circuit current, short circuit power dissipations. And one thing you can know from here is that we can actually, from our design, we can reduce dynamic power dissipations. Leakage also probably we can, but hey, if the process is defined, we can't do anything much. So leakage also is nearly out of a designer hand. Short circuit currents also we will discuss. There are probably some way by a designer to reduce that, but for sure dynamic power could be reduced by a designer. Why? Because dynamic, as name suggests, it is the power dissipation when you are changing your signal. That means reduce the frequency of the signal, imply less dynamic power. Yeah, I will explain this thing, but here we can't reduce the frequency because we want a great performance SPD device, which means a great frequency response, but we can do something to reduce this dynamic power. But before I discuss about dynamic power, you need to know one thing, and that is how actually the equation is there, power dissipations. So see how the dynamic power is coming on. If we consider that our only the PMOS is on, that means at the signal we have a low logic, zero logic, and our output was at zero. Output is at zero, imply the capacitance which we have at the output node. Just recall our earlier classes that I have actually explained how this CL is coming. This CL is basically from the capacitance it will see when it will connected to some external circuit, plus the wire capacitance, and plus its own capacitance of an inverter. There are three components, and those are written together in a CL. So in this case I am considering that hey, my CL is 0, I have provided a 0 or a low input, then our PMOS will be 1, PMOS will get a direct path to charge our capacitance, and therefore our capacitance is charging, which imply that we have given a 0 input here, but here our capacitance will go into a high voltage zone, or imply we'll get a in the output 1 or the high, and that is the work of a inverter, why we are using an inverter. Now anytime you are charging your capacitor, imply you are throwing some power, you are drawing some power from VDD, because a current flow will be there. So how to find out that equation? So if you probably remember this one, that your CV is equal to Q. That means for a C capacitance and a V voltage, we need to bring a Q charge to charge our capacitance up to VDD, right? And your power formula, you have P is equal to VI, right? Or you can again say that your V is equal to Q by T, charge per time is your current. Or you can see that your Q is this, so that means your total power which need to be drawn from VDD, and that is V by T, and Q is already CL by VDD, and this is also your VDD, because we are drawing power from VD, which imply the power we have, and that is CL VDD square by T, or the energy which is power into time, it is your CL VDD square. So that is the energy we are drawing from our VDD. That is the currency actually. If it is less, our circuit will sell more. If it is more, then people will hesitate to buy our product. Yeah, performance, they need performance, but again, power is a very sensitive topic considering the smartphone, the laptop era. Now the question is that we are drawing CL VDD square from our power source VDD, but how much energy is exactly stored by our capacitance? And in your surprise, it is actually half CL VDD square. How I get this thing? I get this thing easily by just integrating power with time. So here it would be voltage across your capacitance, and that is your V out, which is dependent on T, because as time increases, V out will also keep on increasing. Then your current flow, which is also a function of time, because current flow will come down as our capacitance will charge, and dt. And if you do this integration, then you can easily find out this one. If you can't do this integration, I'll strongly suggest you please revise your integration. It's all okay if you forget, no issue, but this is also not necessary for our interview purpose. So it is just if you want to prove it, then you can do this integration. So that means we are drawing a power, for example 10 unit, but we are storing a power of 5 unit, where the half unit is going, and that is actually getting dissipated through your PMOS as a heat. And you can clearly see here that the resistance of your PMOS, right, it's not coming into picture here. And resistance of PMOS means the W, the wide, how much wide your PMOS is not coming into this picture. So then how to reduce this power dissipation? One easy and great way to reduce power, and that is reduce this VDD. If your VDD is 5 volt and you are reducing it by half, that is 2.5, then you have a square effect. 5 into 5, 25, 2.5 into 2.5, 6.25, huge reduction in power. And actually this is one of the reasons why we want to build NMOS or PMOS or CMOS smaller and smaller, reduce the gate length smaller and smaller, because the smaller the device, the lesser VDD would required. But here also we have a catch, and that is if you reduce VDD and keep on reducing, then the performance of your circuit will degrade. If you just recall our earlier discussion, there I have discussed that your propagation speed, your TP, the delay by which it will rise and the fall, rise time and the fall time will increase if you reduce the VDD, and if you increase the VDD, then rise time and fall time will decrease also. So that means we can't go on reducing our VDD. There is a hard limit, and maximum of time when you design a circuit, actually there is an external dependency which will say, hey, you can use only 1.25 only, you can't go down than that. So that means VDD is probably not in a designer hand, most probably, right? So then what are extra thing we have, and that is you can reduce your CL. That is a huge, that is a like most important thing, and there the PD engineer, the physical design engineer come into play, because their layout will decide how much capacitance you have, right? If they here, for example, your CL is also depend on the external wire. So if he or she draw a long wire, then there will be more CL, more power dissipation. So that's why layout engineer need to be very efficient when drawing this layout. So by efficient layout we can actually reduce CL. There is some other way also, like here reduce the NMOS or PMOS, because if we reduce them, then directly they will reduce our capacitance, but again this will degrade the performance of your circuit, because the current flow between that device will drop, which imply the charging and discharging time of your capacitance will increase, imply your TP, rise time and fall time will increase, imply your performance will decrease. So there should be a balance between the power saving and the performance. And anytime we try to design anything, we get the specification from our user that what would be the lower limit of performance they want and what would be the best scenario to save our power. So if your interviewer asks you that, hey, you need to design a low power device, tell me what are the way you can reduce, then you can explain these two things: reduce VDD if possible and do a efficient layout design so that our CL could be reduced. There is another way, and that is reducing the frequency of your signal, but not directly. We can't directly reduce the frequency of our signal, but hey, how to relate frequency with the power? And let me help you there. See, our power dissipation is CLVDD square, and that is through one cycle going up and down, right? So if this thing keep on happening, then that means you will keep on drawing CLVDD square power. And if this thing happen for 5,000 million time in a second or for 5 megahertz, so that means your total power dissipation would be VDD square and then the F, the frequency, or it would be your 500 megahertz. So for 500 megahertz, if you keep on drawing power for each of the cycle, then you will consume this much of power. How much of power? Let's get some number. For example, if we have a CL of 1 femtofarad, and yeah, that is a perfect number actually, 1 femtofarad, and probably let us use a 2.5 VDD, so 2.5 into 2.5, and also your 500 megahertz. Then if you calculate it, how much, let's do it. So it will be into 5 into 10 to the power minus 7, and if you do further calculation, then so it is roughly 30 10 to the power minus 7, or roughly 30 microwatt. This is for only one CMOS inverter. If you have 1 million CMOS inverter, then this is your 30 watt. It is a huge quantity considering our smartphone or other handheld device. But here we have considered that your 1 million gate each will toggle their output for each of the signal 500 megahertz, but that is not the case. The architecture designer, what they do, they actually design the circuit in such a way that each of the gate will toggle the minimum time. Actually, there are some practice questions also actually we have. I will try to bring them, by which you can decide, like for example, this is your CMOS circuit, and you have A and B and A and B, and you know how many times A and B are toggling. Then we have an algorithm by which we can assign the efficient way by which will reduce the power also. So in summary, we have three ways. One is in the architecture level, that hey, reduce the toggling of the signal for each gate, okay, and second would be reducing the CL by efficient design, and last would be reducing your VDD. So these are the major way. If you know some other way also, please comment it down, and I'll see you in our next video. Till then, tata, bye bye.